Hey everyone, my name is Rochelle,
I'm Aaron.
And I'm Kabir.
and today we'll be discussing climate change's effect on weather trends in Virginia. So as we know, climate change can have tremendous effects on the environment, and we've seen this just this year in Virginia as well. So here we have an image of record levels of rainfall in the Chesapeake Bay. And we can see this boat got destroyed and there's trash everywhere on the beach. And here we see flooding in Virginia Beach. And you can see like some people are drowning and it's very dangerous and there's been a lot of loss of life and housing and infrastructure as a result. We also see increasingly frequent thunderstorms in northern Virginia, which could also be very dangerous. So a little bit more background about the issue of climate change. Um, these impacts are no longer limited to the polar regions, and rather they extend to every corner of the globe. And even in Virginia, we see that we see these changes and irregularities in the weather patterns. And a lot of people will call this global warming, but global warming is kind of a misleading term because it's not just that the average temperature of the globe is increasing, but also that we're seeing more catastrophic and extreme weather, just from the examples we've seen in the previous slides. And we hope to develop a model that predicts weather based on thousands of collected points of weather data, and we hope to use this to improve the accuracy of future weather predictions. Uh, Furthermore, we hope to analyze the impact of climate change on global weather patterns, and we will be analyzing a data set to see if there's a trend in more extreme weather. We'll train several regressors that will be used to predict temperatures based on any patterns that occur in the data. And the variable that would be primarily looking to predict is daily air temperature, as it is the easiest and most directly impactful unit of measure because it's useful in many biological and chemical processes, and there is a strong necessity for consistent temperatures, or these processes will fail to function effectively.
So the data we used to train our models in this project were collected by a weather station in Virginia in 2006. And this data set is only used as a proof of concept since it provides a lot of detailed information about the weather besides just the temperature and the time the sample was taken. We'll see this in the next slide as well. And by feeding as much relevant information about the weather as we can, we're able to get a more accurate model than if we only use the temperature. So here we can see the many different measurements taken by the sensors at the weather station. So most of the data that we just saw was recorded in standard numerical values. One value that wasn't recorded in simple floats or ints was the date and time. So to solve this issue, we had to convert the date time into Unix time so that we could sort of have a linear scale for the time, and the model could learn using simple chronological pieces of data.
So essentially in our methods, we applied this transformed data to 3 supervised learning models. The first among these was the linear regression model. A linear regression is simply a linear approach to modeling the relationship between a scalar response and one or more explanatory variables. This was the most simple to implement and plot among all the models we made. Following this was the decision tree. This model serves as a decision support tool that uses a tree-like model of decisions and their possible consequences. And then the last was an SGD model, stochastic gradient descent model, which is simply a more efficient version of the linear regression. And then along with this, we implemented feature engineering, and we found that the variables of wind speed and average wind speed were similar, and thus we chose to remove the wind speed feature from our data set. We also created a correlation matrix and identified several features that could be combined. And then here we have our plotted models from left to right. I'll read. It's first we have the decision tree, which is very closely models the actual data. The model, the trained model is in the red dots, and then our actual test set data is represented by the black dots. So moving from left to right, you can see our decision tree appears to be the most accurate of the three, while our linear regression model seems to be the least accurate. And then we also recorded the root mean square errors for each of them. And then we have a plot with all three models and the actual data to this side. So our lowest one was the tree, the decision tree. However, indicated by the 0 RMSE value, it's clear that this model overfit. So overall, our most accurate model was indeed like the linear model. So what can we take away from this? From the graphs, we notice a trend of temperatures becoming more volatile as the months go by. And this corresponds to what we would expect due to the impact of climate change. And then, like I said earlier, the decision tree model appears to overfit the data as it sticks very closely to the test set. And then the SGD model appears to capture the variance in temperatures the most accurately. And this is reflected in those error rates.
Surprisingly, our biggest challenge didn't have to do with the machine learning model training at all, but rather with converting the data into an appropriate data type. So we saw this especially with the date time. When we were transforming this into a numerical value, it was being recorded as an object type rather than an int or a float. And this caused many problems early on with the training, since we didn't actually realize what the issue was. But once we realized that we needed to cast this value as a number, we were able to find much more success. So why should we care, right? So our results reflect what we expected from the onset of the project. And our expectations were based on what we know about global warming, which is that it's causing more irregular weather, and the effects of climate change are compounding. So in the coming years, the weather patterns that we see in Virginia will get a lot harder to predict. And this is why we have to start paying more attention to the weather now. And in this project, we've taken the first step by exploring which models are best for this type of study. In the future, we'd like to spend more time determining which models are optimal besides the ones that we used in this project. And we'd like to combine them into an ensemble model so that we have the most accurate model possible. And here are references.
Thank you.